So, hello everybody. Welcome to our talk titled Real-Time Inference of Neural Networks, a Practical Approach for DSP Engineers, Part 2. So this talk is labeled Part 2 as it is the continuation of a talk we have been giving as last year's ADC. And there we presented the plugin template for neural network inference in real-time audio environments. But don't worry, if you did not attend to last year's talk, we're going to provide a brief overview of the key points in this presentation. So first, some words about us. My name is Schulz. I'm a researcher at the Audio Communication Group at the Technical University of Berlin. There I'm the head of the research team Computer Music and Sound Synthesis, as well as the TU Studios there. My main research interests lie in real-time audio environments, in neural networks for audio effects and sound synthesis, as well as mixed signal audio processing.
My name is Valentin Ackva. I work as an audio software developer at a real-time speech enhancement company, Inference, and there I'm mainly responsible for developing traditional DSP and AI-based audio processing like audio super resolution and denoising. And besides that, in my free time, I'm also doing a lot of music-related audio development, mostly open source.
Okay, so let's come to the contents of this talk. We're going to first have an introduction to the topic. Then we're going to examine the real-time violations of the major inference engines. We will then present our architecture from our new library. Then we will dive deeper into two topics, static thread pool design and minimizing latency. Then we're going to talk about how different factors impact inference runtimes from these inference engines. And finally, we will conclude our talk. So we have quite some topics to cover. Let's get started with the introduction. Neural networks have become an integral part of today's audio signal processing. And to integrate them in real-time audio environments, we need to follow a pipeline. And the first step of this pipeline is training the model, and this is mostly done in a high-level programming language like Python. Then we need to export the neural network model, also mostly done in a high-level programming language like Python. And finally, we need to implement the model in a real-time audio environment, and this is mostly done in a low-level programming language like C++ for performance reasons. And we're going to focus on that step. And this can be done either by writing the inferences ourselves with the standard library or eigen, or using specialized libraries. And that's what we are going to do. And we are going to focus on the major three inference engines, Onyx Runtime, libtorch, and TensorFlow Lite. But unfortunately for us real-time audio programmers, these engines favor average execution times over worst-case execution times. So none of these engines actually gives any real-time safety guarantees. And we also found some confusion about this topic in the literature and also in the industry. And for example, Chowdhury found in 2021 that none of these engines are actually real-time safe. And Stefania et al. Concluded 1 year later that they are real-time safe after the first inference, but only for dense layer networks, neural networks for audio classification. It is noteworthy that there exists a real-time safe library called RT-Neural, which is great for small networks, but unfortunately it has a very limited layer support. So we are going to focus on the major three inference engines. So in last year's talk, we had been giving an outline of the pipeline for implementing these neural networks in audio plugins. We have given also an overview of the major inference engines, showcasing their strengths and weaknesses. We have then presented a real-time safe plugin template within the JUICE framework, shown some basic benchmark on one specific neural network model, and then had some discussions about continuous signals and streamability of neural networks. And in this talk, we're going to continue where we left off. So first, we're going to shed some light on the question of real-time violations of the major inference engines by quantifying them. Then we're going to present our new cross-platform library called ANERA, which stands for an architecture for neural network inference in real-time audio applications. This is the continuation of our plugin template and streamlines the use of real-time of neural networks in any real-time audio application and is independent of the JUICE framework. This architecture also has significant improvements, and especially for the use of multiple instances simultaneously. It has a much refined latency calculation and has built-in benchmarking capabilities. And finally, we want to show you how various factors impact the performance of the inference engines.
Okay. Considering all the discrepancies in the audio domain regarding whether these inference engines are real-time safe or not, we decided to take a closer look at this topic, and we would also like to show you how we approach this. So this brings us to an important question, and that's how can we check for real-time violation executed by external shared libraries? And for that, we employed the so-called real-time sanitizer, or shortly called Artisan. And this tool is part of the CLang compiler and runtime library, and is designed to help us to catch real-time violations during code execution. And actually, the creators of Artisan presented their tool at this and last year's ADC, and we highly recommend checking their talks out. In short, how does it work? We compile our code with the Artisan flag, which is signaling the compiler to instrument our code for real-time safety checks. During linker stage, Artisan replaces certain non-real-time safe operations like memory allocation and thread operations, and replaces that with intercepts from the Artisan library. And now we can run our executable, and with that we are able to quantify our violations and also check the types of the different violations. And this setup also allows us to monitor violation executed by external shared libraries, which is really important in this case. So how did our test setup look like? We selected the three major inference engines, Onyx Runtime, libtorch, and TensorFlow Lite. And for each of these engines, we exported three distinct neural networks that are commonly used in the audio domain. So a convolutional neural network, a recurrent neural network, which has an internal state. Stateful operations are not supported by design by Onyx Runtime, so we excluded that from the test setup. And we have a hybrid neural network, which is a combination of the prior two. Each model engine combination was executed for 50 iterations to also see how the violations behave after first inferences. And we actually only monitored the inference callbacks, so no model loading or pre and post processing was involved. And we got the following results. Generally, we can say none of our inference engine is real-time safe, even after first inferences. And the scale of the plots can be misleading here. So none of these graphs ever reach zero violation, but because we have such a large range in the y-axis, it could look like that. So to give you some numbers, let's look at Onyx Runtime. Here we have slightly higher violation during the first inference, and afterwards consistent violations. And here the CNN model has roughly 140 violations each iteration, while the hybrid neural network has over 8,000. If we look at libtorch, we have really high number of violations during the first three inferences, and then consistent violations ranging between 3 and 10,000 violations each iteration. For TF Lite, the hybrid and CNN model have quite low numbers, roughly around 100, while the stateful model seems to be not very optimized here and has over 100,000 violations each inference. Also in general, Onyx Runtime and TF Lite only conduct memory-related violations, while libtorch also has some thread-related violation. Even we configured libtorch to only use one thread. And we wanted to share these findings because we have seen or heard that many implementations let this engine run on the real-time threads. And for some people, this seems to work quite well, and they are successful with it. But we don't feel comfortable with that. And so we hope that it's clear now why we feel that way. Now we have identified these real-time safety issues. Let's dive now how we address them. And here we show you how we integrated those engines in our application and which design choices we took on our right. So last year, we already proposed a solution for it, which looks like the following. On the left side, we have our real-time audio thread where our audio application is running. And this audio application spawns an inference thread on the right side. And in between, we have some thread-safe ring buffers that can share data between those threads. And the inference thread will now constantly check the ring buffers if we have enough samples to start one inference. And if so, we do a pre-processing and then the inference. And after we proposed the solution, someone asked, hey, how do you handle if you have multiple instances of your application? And well, our implementation works well with some instances, but if we have a really high number of instances, we could find a better solution. And yeah, why can't we find a better solution? Let me first illustrate what's the underlying problem here. So on the left side, we have our operating system where our DLW is running. And let's just imagine this DLW just spawns one real-time thread. Besides that, we also have our message thread, which is doing the UI. And on our DLW, our AI plugin is running. On the right side, we have 4 logical cores, and this whole setup should work nice and smoothly. But once we start adding more and more instances, for example, here 3, now we have 4 high-priority threads running. And I think this setup should still work quite good. But if our operating system now also handles other high-priority background tasks, then we could already run into some problems. But now we even add more and more inferences. So we have now 7 real-time threads or high-priority threads running. And now our cores are really heavily used. And we run into a problem that is called oversubscription. So what is oversubscription? It means if our number of high-priority threads is larger than the number of logical cores. And this can cause our threads to compete for each other for the same cores. And our operating system must frequently interrupt these high-priority threads to give each thread a chance to spin. But this can lead to reduced performance, as the threads do not get continuous access to CPU time, resulting in delays. And this can be especially problematic for our real-time processes, which could result in audio dropouts. And because we don't know how the operating system has handled these situations, this might not be the best solution. And therefore, we want to propose our new architecture, which utilizes a static thread pool design. And this design allows us to share inference threads across instances, which can be plugins, either instances of the same plugin, or even different plugins that execute the neural networks. And this means the first instance of our application will create a thread pool, and all future instances will use the existing one. And this design also has another advantage. For example, we have just one instance running, which spawns 8 inference threads. Then we can utilize those 8 threads to also parallelize our inference and therefore get faster runtimes. And yeah, in order to be able to share that static thread pool across multiple instances and plugins, this needs to require us to develop a dedicated library. And yeah, so we did, and we want to show how we build it. So let's start with the most familiar component, our audio application, which is split in 3 parts: the constructor, the initialization callback, and our real-time audio callback, where we process the data. Now here in the constructor, we also have to initialize some objects we need for our library, which is a pre- and post-processor, depending on our model needs, and an inference config, which defines the configuration of our neural network model. In the next step, we introduce our thread pool. This pool is part of our static context class. And how are we going to share data between those classes? For that, we provide an easy API, which is called the inference handler. And here you just pass over the configurations in the constructor and submit the host audio configuration. And once initialized, you can start processing the audio in a thread-safe manner. Internally, the library passes over the data to the inference manager. This class is responsible for calculating a reliable but minimal overall latency of our library, and also ensures that our output audio data is time-aligned to the latency we just calculated. Moreover, when the class is created, it also requests an instance of our thread pool or context class, which means if it does not exist, we create it. Otherwise, we use the existing one. The inference manager also creates for each instance a session element. Once this class allocates all memory before the audio callback starts. And it is responsible for receiving all the data from our real-time audio threads, as well from the inference threads. And it will store it in our ring buffers. Then we have also additional pre- and post-processing here. So some neural network models require model-dependent pre- and post-processing. For example, gain normalization before doing an inference. And we also introduce some timestamps here in order to ensure that we process the data in the right order. And this all happens on the real-time thread. And how do we now communicate with our static thread pool or inference threads? For that, we provide thread-safe structures that are just responsible, that never two or multiple threads can access the same data at once. And once the real-time thread submits audio data, the inference threads can start accessing that data and do the inference. So what if you want to use the library? What are the steps you have to take in order to use the library? And it's really simple. You just have to define an inference config, which has the basic parameters of the neural network model. Then, if the model requires this, define a custom pre- and post-processing. And if you want to specify the thread pool, you can also pass in context configuration. And everything else will be handled automatically by the library, regardless the neural network type. Which parameters do you have to submit? Well, there are some necessary parameters like submittal model data, what is the shapes of our input and outputs, and define the maximum inference time of our model, which we later will dive a bit deeper. You can also submit some optional model configurations depending on the model. So if the model has an internal latency, you have to submit that to take it into account. You can warm up the inference stage. You can also use the library with multi-channel neural network models, which you have to define here. And there are other parameters, and you can look them up in our documentation. And there's also the context configuration, where you can define the number of threads that is used in our thread pool. If we look at our code, it's just 20 lines. So we first define here our inference config. So we say here we load an Onyx model, and we say that with inference backend Onyx, define the input-output shape and the maximum inference time. Then we just prepare a default pre- and post-processor, hand it over to the inference handler, prepared with our host audio configuration, and then we can already access the calculated latency. Then we just select a backend and can start processing the audio in a thread-safe manner. As I just said, some neural network models require custom pre- and post-processing, and this can be also achieved with Anira. So some neural networks might need more input or output tensors that not only have audio data, and for that we also provide thread-safe mechanism to submit or retrieve those informations from the real-time thread. So for example, here on the right, we have an input for a neural network, which has next to the audio data also a parameter, which could be, for example, just a gain. Or the example 2 gives out the output data, and next to that, a prediction of anything we just calculated in the neural network. With that, we come to the last slides. These are our supported inference engines, Onyx Runtime, libtorch, and TF Lite. And we also have a custom backend already implemented as a blank template. So if there's any inference engine that is missing, you can easily integrate it to our library. And if you want to modify one of the existing engines, this can be also done there.
Okay, thank you, Valentin, for the overview of the architecture of our library. So I want to dive deeper with you now into specific topics, the static thread pool design and the latency minimization. So first, we're going to talk about the static thread pool design and how we handle the inference job submission. So we are going to focus on this part of the library here. So Valentin has already mentioned we have these thread-safe structures that are used to pass over the data between the audio thread and the inference threads. And to guarantee that only one thread can access the data at a time so that we have no data races, we use standard atomics. And these standard atomics lock the data inside of these thread-safe structures. In order to coordinate the job submission to the thread pool, we use a thread-safe queue. And how does this work? It's actually pretty simple. After finishing the pre-processing, the audio thread enqueues a new inference task to that queue. In this example here, the audio thread has already enqueued 4 inference tasks. Then our inference threads will constantly check the queue and try to dequeue a new task. If a task exists, it will dequeue the oldest task in the queue and infer it. So our inference threads will work their way up until the last inference task here is dequeued and inferred. And then our queue is empty. And we will need to wait for the next process callback in the audio threads to enqueue a new task, if we have enough samples in order to fit them in the model input size. And during this time, we will constantly try to dequeue a new task. And since we have multiple threads, all these threads will try to dequeue a new task in a loop. So they will try to dequeue and do that in a busy loop. And a busy loop can actually be very problematic if this is done on high priority threads. So this can lead to maxing out the load on the logical cores where the inference threads are running on. So what do? We are lucky because there has been a great talk at ADC 2020 by Timur Dumla about the safe usage of spin locks. And Timur adapted a solution from the Linux kernel, which he called exponential backoff. And exponential backoff means we have different phases of waiting for our lock, or in our case, of waiting for our new task. So this is the way we implement it in our library. In the first phase, we will try to dequeue a new task in a busy loop for 4 times. If we do not succeed in dequeuing this task, we will enter a second phase. We will have a pause instruction and then try to dequeue a new task and do that in a loop for 32 times. And during that pause instruction, other processes from the operating system can do their job. And then, if after 32 times we do not manage to dequeue a new task, we will enter a next phase where our pause instruction will be even longer. And so on and so on. And so this is the concept of exponential backoff, and it helps us to leave resources to other processes and not max out our cores that we have. And if you're interested in the topic, I highly recommend you to check out Timur's talk. And then we thought, actually, there might be an even better solution for the coordination of inference tasks, not spawning any threads at all and relying on our host threads, the threads from the DAW, for example. Because imagine we have different manufacturers that all spawn their own threads for audio processing and inference of neural networks because they don't all use the Anera library. So then we can run into the problem of oversubscription again. So we hear the new plugin format clap has a feature that allows host-provided thread. So is this something for us? How would be our ideal solution? So after the preprocessing, after having this preprocessed thread-safe structure, we could request the execution of this inference task on the threads provided by the host. So we had a look in their documentation of the thread pool extension. So that's the way in CLAP it works. There are extensions. We had a talk here. So we read this and read, we can schedule numped task jobs in the host thread pool. So we thought, okay, great, that's something that's for us. But it will block until all the tasks are processed. So that's not what we want, because we want to submit a task and then keep on going. And then this must be used exclusively for real-time processing within the process call. So at the latest, this is the spoiler, we cannot use that. It's a bad idea for our purpose. But we have been actually talking to the CLAP people here, and we're asking for an extension where the host would provide high priority threads, so less priority than the real-time threads, but still high priority threads that would be available for using for non-real-time safe operation. For example, inferring these inference engines. And let's see what happens. We will try to submit a pull request and see how this goes. Okay, so enough with the static thread pool design. Next topic, minimizing the latency in our library. In general, we have 4 different factors that influence the latency in our library. We have the host buffer size, we have the model input size, we have the model latency, and the maximum inference time for one inference. So this is the runtime which is dependent on the system we run on. So let's have a look first at the first 2 influences. So the host buffer size and the model input size. We often face situations where the host buffer size and model input size don't match. So this leaves us with a reminder when we divide the 2. And this introduces a latency since we cannot process all the data in the first run. But this is a known issue and has been addressed already by Let's in 2001. And he proposed a method called callback adaptation techniques to minimize this latency. And this works effectively by calculating the largest reminder of n times a divided by b until the pattern repeats. And in this example, a could be our host buffer size, and b is our model input size. And we define the largest remainder here as h-adapt for our future latency calculation. And we have built up upon that idea and thought, okay, so we have this pattern. We know the pattern is going to be repeated afterwards. So we can calculate the maximum number of inferences that we can start for one host audio buffer. And here one host audio buffer A. And we can see for the third host audio buffer, we can actually start 3 inferences. So we take that number and multiply it with the maximum inference time for one inference, and we call that I max. And then we already receive our final latency calculation to minimize the latency. So we take h_adapt, add this maximum inference time, we divide it by the host buffer size, round it up to the next integer, multiply it with the host buffer size, and add the model internal latency if there is some. But since we round up the term in the middle here, we will always end up with at least a latency of 1 buffer size, which makes sense since we are on the audio thread. When we are on the audio thread, we submit an inference task, and directly afterwards we ask if it's finished, so we don't have any time to process. Okay. So we thought for some applications this might not be acceptable. And therefore in Anera we introduced some optional controlled blocking operations to further reduce the latency. These introduce minimal real-time violations to maximize the time we have available to receive data from the inference threads. And they are implemented by using the try, acquire, until method from semaphores, and they are disabled by default. So by default, we also don't use any semaphores at all because semaphores are not real-time safe, especially the semaphore release method. So this is a highly controversial mechanism, and I'm sure I got some of you triggered already, but let me still explain how this works. So we know the time it takes for us to process one audio block. In this example, it's 10 milliseconds. And then we use a share of this number, for example, half of this time, in order to acquire a semaphore with the next inference result. So this maximizes the time we have available to receive data from the inference threads. But now imagine we have 2 plugins in series, both waiting in the audio callback for half of the time. We already enter some serious problems here. But on the other side, if we are in controlled environments like embedded systems with only one instance, this could be a useful method to further reduce the latency. But still, we want to point out that in this case, our high priority real-time audio thread might waste some valuable resources, depending on the OS scheduler, how he handles this semaphore try, acquire, until method. So actually, we are considering even to give a possibility to the user of the library to make some other processing on the real-time audio thread while waiting for the semaphores. But anyway, if we consider all of that, this allows us for some configuration to add an additional latency of 0. Okay, so now we have been talking a lot about the maximum inference time, and we want to now talk about what are the different factors that influence the inference runtimes of these inference engines. For this, first we need a method to measure inference runtimes reliably in real-time audio environments. And Anera has a built-in benchmarking tool that allows us to measure the inference runtimes of different configurations. It is designed to emulate the real-time audio environments and takes arguments like the buffer size, the backend we want to use, a neural network model, how many repetitions we want to do, and many more. And this allows us to measure the inference runtimes of different configurations in a single benchmark. And how do we actually emulate this real-time audio environments? Well, we first construct an instance of our Anera inference handler with a specific configuration. Then we sequentially process a defined number of buffers. And these buffers we are calling iterations here. And after that, we destruct the Anera inference handler instance and repeat the process for a defined number of repetitions after switching to the next configuration. Okay, so we use these benchmarking capabilities to measure the inference runtimes of many different configurations. We have the systems here, so those are hardware and operating systems. We have our different inference engines. One of these engines is the bypass engine. This is a custom engine where we bypass the inference stage on the inference threads. Then we have different models here. So the 3 model architectures that Valentin has shown already. a hybrid neural network model, a recurrent neural network model, and we have 3 differently sized convolutionary neural network models. And then we have benchmarked different buffer sizes. All of these configurations have been run 10 times, and we have always done 50 iterations. This gives us in total more than 200,000 measurements. And we took all of these measurements, modeled them statistically to find out which factors have a significant impact on the inference runtimes. All the methods for the statistical modeling are described in detail in a paper which Valentin will show you later. And we are going to focus on the results here for time reasons. So what did we find out? The inference runtimes are actually significantly influenced by many factors. So this plot here shows a comparison of the inference engines. On the y-axis here, which is the same for all plots which are going to come, we have the estimated marginal means of the inference runtimes per sample. So that's why RPS, runtimes per sample. And if you're not familiar with the term of estimated marginal means, you can just think of it as average runtimes per sample. So first, let's have a look at the non-engine. This is this bypass engine where we bypass the inference stage. We can see it's significantly faster than all other engines, which is no surprise, but it shows our library, even with pre- and post-processing, does not adds very little overhead. If we have a look at the actual inference engines, we can see that for the stateless models, Onyx runtime is significantly faster than the other 2 engines. Onyx runtime does not support stateful models, so in the RNN it is excluded from the comparison. If we compare libtorch and TF-Lite, the situation is a little more interesting. So libtorch is faster than TF-Lite in the big convolutionary neural network, in the recurrent neural network, but for the hybrid neural network, TF-Lite is faster than libtorch. So next, we have done a comparison of differently sized convolutionary neural networks. And also here, we see apart from the smallest neural network model, Onyx runtime is always significantly faster than the other 2 engines. Only for the smallest neural network model, we see no significant difference to TF-Lite. But interesting is again the comparison between TF-Lite and libtorch. In comparison to TF-Lite, libtorch becomes faster the bigger the CNN model gets. So for the small and medium-sized CNN neural network, TF-Lite is actually faster than libtorch, and for the big CNN network, libtorch is faster than TF-Lite. This could also be the reason why TF-Lite was faster in the hybrid neural network model, because this one had very small convolutional layers. Okay, enough with the inference engine. Let's have a look at another factor. And let's have a look at the influence of the iteration index on the inference runtimes. And the iteration index, so remember, this refers to how many buffers have been already processed after we have constructed our Inera library. And let me explain the plots a little more in detail here. So on the y-axis, again, the estimated marginal means of the runtime per sample. And then we have these dotted lines, and these dotted lines represent the average over all iteration indexes for the different models, and here engine-wise the plots. And if we had a significant deviation from the average, we put a star here in these plots. So if we have a look at libtorch, we can see that all first inferences with libtorch for all different models that we checked had a significantly higher runtimes than the average. And if we have a look at Onyx runtime, we can see a similar trend, although it's not significant for the hybrid neural network model, and some alternating pattern for the convolutionary neural network model. So then we compared these plots of libtorch first with the plots of the real-time violation that Valentin had shown for libtorch. And actually, we found some sort of similar pattern. The first inferences, where we had a high number of real-time violations, actually had a higher number, had significantly slower inference runtimes. And therefore, we could think that these real-time violations in the first inferences could be a reason for the slower inference runtimes in the first iterations. Therefore, in these cases, we would actually recommend to warm up the inference engine in the constructor before doing the first inferences in the process callback. So this is the option which we have in the Anira library, warm up inferences. And there you can actually define a number of inferences because you see that not only the first inference is significantly slower than the other ones. If we do the same comparison for Onyx, we can see, for example, the alternating pattern here in the CNN. It's not reflected in the real-time violations. So we can conclude that the real-time violations are not the only reason for differences in the inference runtimes per iteration. Okay, so now we have a look at the last factor. We want to know how is the influence of the buffer size, and in all of these benchmarks, so Anira supports different buffer sizes and model input sizes, but in all of these benchmarks, the buffer size was equal to the model input size of the model. So how does this factor influence the inference runtimes again? And first again, let me explain the plots to you. So we compare neighboring buffer sizes of the same inference engine, and if there is a significant difference, we put a star in the color of the inference engine on top. So for example, we compare Onyx runtime inferring a buffer size of 64 and 128 samples. And we can see, oh, it's significant. So we put a star in the color of the inference engine on top. And although we make these comparisons engine-wise, we can see a remarkably consistent trend across all engines. And this trend is the higher the buffer sizes or the model input sizes, the faster the inference runtimes get per sample. And this trend is really strongly pronounced for the small buffer sizes and get less pronounced for the bigger buffer sizes.
Thank you, Faris. So now we reach the last chapter where we conclude with a summary of the library's features and want to show you how to get started with using the library. So first of all, let's wrap it up. Anira is a thread-safe inference engine wrapper library, which supports all major inference engines used in the audio domain. And the library is compatible with various types of neural networks. So if you have a stateful, stateless model, or a model with extra input and output tensors, we have you covered. And generally, every model that is real-time capable should be able to run in Anira. And yeah, the library can handle all of these various types simultaneously. So the static thread pool design can handle processing different models. The whole library is written in modern C++20, so it should be easy to integrate that into any application or programming language. And we also support Linux, macOS, and Windows, and also almost all processor architectures. And yeah, the library has a permissive license, which should also make it easy to integrate. So why did we actually wrote this library? And when we began developing or deploying neural networks into real-time applications a few years ago, there were actually really few resources out there how to do it effectively. And developing an effective solution requires expertise across several domains, like log-free programming, multi-threading processing, static designs. You also need a lot of DevOps to integrate those libraries into your projects, and of course, machine learning. And we also worked with quite a lot of machine learning engineers, and they don't even think about real-time principles we often facing with. And therefore, we wanted to develop the library to offer an easy-to-use solution that lowers the barriers to integrate neural networks into real-time audio applications. And yeah, how can you get started? When you want to use the library? And as a starting point, we provide 5 different neural network implementations, which are also very common used in the audio domain. And for each network, we provide a machine learning implementation in Python. We provide it as implementation in TensorFlow as well as in PyTorch. So whatever your background is, we have you covered. And we show for each network how to train it. And for that, we also provide the training data. And we also have the pre-trained models of these networks. And then we show you how to transfer these models to a real-time application. And we show that by providing an example with an audio plugin using the Choose framework. We have a native clap plugin that's doing that. And if you're from the embedded world, we also have a beta application example. And we want to add more and more examples to that. So we're currently working on a check client and a Max external. And yeah, we also provided some example benchmark examples. So actually all the measurements we did previously in the chapter, we have an example how we did that. So if you want to benchmark your own model, it should be a quite easy point to start from. As far as that, we also published a paper about our work a few months ago. It's accessible at the IEEE Explore. It rules out a lot of what we presented today, but in more details. And also, we explore more how we did the statistical modeling there. Here's the link to our library repository. It contains the library itself, as well as all related documents and the examples. And we invite actually everyone to contribute to this library. Or if there's any feature missing, let us know and feel free to open a feature request. With that, we come to an end. We thank you for listening. If you have any questions, we are happy to answer them. And if you have any opinion on that controversial control blocking mechanism Fares showed, also tell us your opinion on that. Yeah.